This would be our 20th lecture. So in the last class, we have covered almost everything that we wanted to discuss when it comes to electrostatics. And I hope that you realize that much of what we tried to do was come up with efficient mathematical methods to solve a variety of problems under what you would call the electrostatic situation. There are maybe a couple of things which I may have not done in the class, but it would make sense to look at it, especially the part on the multipole expansion that you have. So just take a look at it. Otherwise, almost everything is done that I wanted to cover. So the starting point, and it's always good to go back and spend a moment thinking about what is it that we wanted to do and how we started. So we wanted to come up with a general description to describe electric and magnetic fields where anything is possible. The charges can be moving, they can be moving at variable speeds, and all these things are there. However, what we said was that let's start with the simplest problem and try and build up from there. And the simplest problem that we identified was the static situation in which the charges don't move. And the natural extension or the natural question to ask now would be, what if the charges are not stationary? So specifically, we want to know what would happen if the charges are in motion. So this is certainly the next question that, or the next natural question that one should raise. And since we have sort of built up our basic understanding, we may, without even getting into any other thing, we might want to say that just as we wrote, so this was our starting point in the case of electrostatics, which tried to calculate the force, and we know what that force was. So let me not write it, but rather let me drop the index E and try to think about the simple picture where you can have a charge, let's call it Q1, moving with a constant velocity V1, and then there is another charge Q2 moving in some direction with a velocity V2. And we would like to know what is the kind of force that they exert on each other. Can it be a simple electrostatic force that we have written with maybe a slight modification, because we know now, since the charges are going to move at any instant of time, if I were to make this measurement, certainly I would get a force between them. But the question really is, in time, how would this force vary? So is it simple enough, or rather is the problem simple enough to just simply extend our understanding without putting in anything right now? So this is just a brute force way of writing it. So is it even possible to write something like this? And in order to argue for or against such a force, obviously we would like to first make some experimental observations and then try and see if such a force would make sense, or is it something else that comes out because of whatever we observe in the experiments. So let's try to come up with a few simple experimental observations, and these are all related to the experiments that were done at least 100 to 150 years ago, which basically led to the understanding of what you call magnetostatics. So the first experiment that I would like to talk about. And many of these things are very well known to you. So even then, it makes sense to just go and relook at some of these ideas. So let's say that you have two infinite current carrying wires parallel to each other. Two infinite current carrying wires. And these are parallel to each other. There is a steady flow of current. And then one tries to experimentally observe what is the what happens if you bring them close to each other. And the observation is that the wire, the deflection is not this much, but this is just for demonstration, that in fact the wire sort of bends towards each other, or they attract. So even though, and the other observation that you can immediately make is that even though the current is flowing in a certain direction, so charges in motion essentially is current. So this current is flowing in the same direction in both the wires. But then the force that they experience is not along the direction in which the current is flowing, but rather it is perpendicular. And that would be a force that would try to bring both of them together. If you change the situation a little bit, so this is still in experimental observation 1, that rather than having the current flow in the same direction, you've set up the experiment in such a way that they were moving in the opposite direction. And now what one observes in the experiment is that rather than attracting, they repel each other. At this moment, one may even ask the question that, is it really these charges in motion that is leading to such kind of force? So maybe what we can do to check this thought is that we may want to put a conductor, a conducting sheet, in between the two wires. So we know what we know about this conducting sheet is that if there is some electric forces that were to act, then the charges are going to realign themselves. And we have discussed the theory in detail. So by putting this conducting sheet, what we are doing is we are creating charges and then some electric fields because of that on the conducting sheet. And what the experiment shows is that no change happens. So whatever is this force, it is simply coming because of the motion of the two charges. And do not forget this fact that we have assumed the current carrying wires to be infinite. So this would be the first set of experimental observation, which tells us that the force is perpendicular to the direction of motion of the charges. And this word motion in itself is an important factor over here, because as we put the conducting sheet, we realize that there is no change that is brought in because of the presence of the static charges. Let us do another. So this is a parallel development, if you wish, and a separate experiment. So let's say that we have one current carrying wire, and it is in the z direction that the current is flowing. Let's have our axis also, the y-axis and the x-axis. And let's say that we bring a magnet. This is still the infinite current carrying wire, along the x direction. So this is a magnet, this being the north pole and this being the south pole. The magnet is brought close to the wire along the x direction. And again, what one observes is that the wire deflects. This would be the experiment of Oersted, for instance. And the deflection is not along the x direction, but rather this deflection is along the y direction. So this is a completely separate experiment in which the object that is brought close to the current carrying wire, it's not simply a current carrying wire, but it's certainly a different kind of object, which is what we call magnet. And at this moment, our understanding of magnet or magnetic forces, or the force that would be there because of this magnet, is that it should in no way resemble the forces that the electric charges would exhibit on the current carrying wire. But the phenomena looks very similar because of the way in which the force acts. And again, in this experiment, I'll write it one more time. You observe that the force is perpendicular to the, or it acts perpendicular on the current carrying wire. And this force certainly has to do with something else, which would be related to the magnet or the kind of effect that the magnet brings in. And we would call this at this moment, because we are talking about magnet, is that this force certainly is some magnetic force. The third experiment, which is a natural extension of what we just did, is that instead of bringing the magnet and looking at what it does to the current carrying wire, let's say that we have a current carrying wire and the current is going into the page right now. So that's the meaning of this cross. So it's an infinite current carrying wire with the current flowing along the inside the page. And what we try to do is we try to put our magnet at different positions. So let's say I were to put my magnet over here in some direction. But what happens to the magnet is naturally aligns in a direction. Again, if I were to put it at a separate location, which is vertically below this current carrying wire, it again aligns in a certain direction. And I can keep on putting it at different locations. And every time I put in maybe like this, and the magnet deflects in a particular direction. Same over here. So not only does this magnet, it exert a force on the current carrying wire, but also what happens is that the current carrying wire, it exerts a force on the magnet. And whatever is the constituent of this magnet, because right now, even though we know the final answer to this, our understanding is that this magnetic material or magnet that we have brought in, or a magnetic compass, if you wish, then its constituent elements are not the same as those charges that we have been talking about till now. And still there is a force, and the way it is aligning, one immediately realizes that it is still perpendicular. So a current carrying wire exerts a force on a magnet. And every time you make this or do this experiment, the three different possible variants of it, the outcome always is that the force is perpendicular, or the force acts perpendicularly on the current carrying wire or on the magnet. So at this point, one can go back and look at the expression that we had maybe guessed and said that let this be our starting point. And one realizes that even this vector itself, it doesn't make sense at all. And then one has to ask what kind of forces are these. So what we have established this so far is that there is a force, and this force we will call it to be the force due to the magnet, and we'll call it to be some magnetic force. So with F sub B, I'm going to represent this magnetic force. And my observations are the following: that this magnetic force, it is perpendicular. So this sign is for it being perpendicular to both the velocity and also the effect of the magnet itself. And we'll say that it is encoded in a similar kind of field, a similar kind of object that we have been talking about, and we'll call it to be magnetic field. So it is perpendicular to both of these, this being the symbol for magnetic field. And it is also proportional because we are looking at currents and charges in motion. So it is also proportional to the charge itself. So given all this information, we want to come up with a force law, or at that time, the objective was to come up with a force law that has as inputs all these three components, which is the velocity, the magnetic field, and the charge itself. And also the interplay is such that the force itself, it is perpendicular to both the direction in which the charges are moving, as well as what you will call a magnetic field. And the natural way, given everything that we have talked about till now, we can immediately cook up a formula, since it is linearly related to the charge. So I will put a charge, and the way in which so some things that I have not mentioned that maybe you can refine these. Is there a question, or is it the usual thing? Just ensure that unnecessarily the mics don't get. So I know that many are doing something else. So, but even then, at least not distract each other. So as I was saying, this is certainly going to be related to the charge itself. And given our understanding of the way in which the vectors work, I can maybe write a cross product. And this cross product ensures that the outcome is in fact perpendicular to both the velocity and the magnetic field. And this would right now, and later one has to do a lot of experiments and verify if all these things hold true. And over the years, a lot of experiments have happened, and we know certainly that this is going to be true. So we have a formalism, a mathematical formalism rather, to calculate these magnetic forces. You also realize that since it is a cross product of two vectors, so it is going to be a sign sensitive equation. At this point, you may again go back and think about the old problem, which was the electric forces or the electrostatic forces. There what we had was the force is equal to the charge times the electric field, and the electric field in the simplest level of description was there may be another charge which we called a source charge, and what is the effect that it has on a test charge. So this was our starting point in the case of electrostatics. And the immediate realization over here is that what this magnetic force, based on the arguments that we have just made, it is certainly not equal to some magnetic charge times magnetic field. Even though it looks like a very simple statement, this statement comes out of physics. And later, if as we move along, and maybe based on your earlier knowledge, you might know that this is certainly not possible, because magnetic monopoles, they do not exist. Having made all these observations, Lorentz, he came up with a combined way to look at both these forces. So the net force due to both the electric phenomena, which is electrostatics, and this phenomena that we are talking about, we have still not really gotten into and come up with under what situations can one make this observation. All that we have talked about is that there is this infinite current carrying wire. That's all that we have said. And another assumption that is over there is that this current is not really changing at different points. Okay. So this would be equal to Q times E plus V cross. And these are things that you have seen before, you know quite a bit about it. And this is the idea behind the Lorentz force. So I hope that the two pictures are clear to us, that one is looking at a lot of experiments. We have not said anything more than this. All that we have said is, if there are two infinite current carrying wires, this is what will happen. If you bring a magnet close to a current carrying wire, these are the different possibilities over there. That's all that we have said. But with that picture, and then trying to argue about what kind of force can one intuitively write, we end up with this Lorentz force. Or if you are just focused on the moving charges, then it is this magnetic force over here that we have written. And let's assume that this is all right. We know that this is anyway it is right, but let's right now just assume that it is not right. It is all right. So just by looking at this force, but just by eyeballing it, what you can also say, or you can immediately observe, is that if you were to look at this quantity, let me just put a B. It doesn't necessarily have to be. It could be the Lorentz force also. But just to demonstrate or clarify the thought, what you have really is that this is going to be 0, right? Because you have the cross product of the velocity with the magnetic field, and then there's a dot product with the velocity. And since the direction of the first cross product is perpendicular to both V and B, and when you take the dot product, this is simply going to go to 0. But we know what this quantity is. This is our work done. And what one immediately realizes, that the nature of these forces that we are talking about is that it does not do any work. So remember that our definition of work done in the physical context, it was that it is the motion of objects against applied fields, right? And we clearly said that even though you might in an intuitive sense, you might be doing work, but that work doesn't really translate to the definition of work done that we have over here, if the motion is simply perpendicular to the applied fields. So what we learn about these magnetic forces is that they do not do any work. And the reason is because the force is always perpendicular to V. So what can it really do? What it can really do is it may alter the direction in which a particle moves. And what it cannot do is, certainly it cannot speed up or slow down the charge. So it may alter the direction in which a particle moves but cannot speed up or slow it down. Okay, so now what we have done and where we are right now is that we have talked about these experiments. We have now some empirical way to look at these forces. And this construction is for a single charge, because you just have a single charge. But we also know that these situations where you think about the single charges, they are not going to be out there too much. In fact, it's mostly the charge distribution that is what we are worried about. So we may, at this point itself, we may want to extend whatever we have done for a collection of charges, and in particular the continuum limit. Again, the idea is very similar to, or exactly the same as what we have talked about earlier when we moved from a single charge to a collection of charges to the continuum representation, that you look at a small element which has some charge, we call it dq, and then you just calculated the contribution due to that, and then you summed over or integrated to come up with a value for the entire object. So without making a big fuss about it, we know that I can write, I'm dropping this subindex b right now, no point in carrying it. I can write it to be b cross b. And depending on the kind of charge distribution that we have, we input this dq, and that is exactly the same as what we had done in electrostatics. And we will have the corresponding formalism to calculate the force. For example, if you recall, for line charge, dq is lambda times dl. For surface charge, it is the surface charge density times the small area element. And for volume charge, it is the volume charge density times the volume element. So you can just input it over there. For example, if you are thinking about line charge, the force would be equal to, so for dq I'm going to put a lambda dl v cross b. Now what you also realize at this point of time that, and I'm going to write over on the right hand side a little bit, so let me put it over here. So if you were to look at this quantity, which is the line charge density times the velocity, so this would be equal to charge per unit length times velocity is length over time. So in fact, the unit is going to be charge per unit time. So the unit of this is charge per unit time. And this quantity, maybe I can put it here, we represent it as I, and I is here for the current. So charge per unit time, this is what we call as current. So I can substitute for that, and I can write this to be equal to dl I cross b. Or if you want, since the line element and the direction of the current, they are in the same direction, this can also be written as I. All these are one and the same. You can do so just watch out for the following thing, that I talked about line charge, and in the context of electrostatics, whenever we had a line charge, it was charge per unit length. But here we are talking about the basic element that is resulting or that is contributing to this force is current, and current is charge per unit time. There is no per unit length over here. And the same thing happens if you were to have a surface charge density that is moving or a volume charge density that is moving. And correspondingly, you can write. So I'm not going to do the same thing again. So you can write, for instance, if you have a surface charge density, we can write it to be sigma v cross b, and then the integration is over the surface. So surface charge density times the velocity, we write it as the surface current density, and the symbol for that is K cross B dA. And for volume, this would be equal to, just write the final thing right now. J here is for volume current density integrated over the volume. So we can at this point say, great, so we have all these different ways and we are in a position to calculate this force. And we can also identify the two components over here. For example, J over here, which is the current per unit area or the current density, volume current density. That is one factor. And the magnetic field is the other factor. The magnetic field is being produced by something else. It could be the magnet itself, or it could be some charges in motion. And that is acting on another thing. And that is the force that you are calculating. So we can adopt a similar formalism like we did in the case of electrostatics, where instead of looking at the force, we identified the relevant quantity to be electric field, and we took it from there. All our calculation was then focused on the electric field. Similarly, what we can do is we can focus our energy and calculate only one of these, which is the magnetic field. And then whenever required, we can calculate the force by inputting in the other part to it, which is the current density. So I hope that this is clear. And these are all, not some things which are at this level not very deep or profound. But still, I hope that you are able to tie these things together. Another thing that I would like to at least briefly talk about, and let us go back to this factor of the charge times the velocity that we have identified as current. So this is equal to or related to the current. And let us consider the following picture. So let's say that you have some volume, drawing it as a cylinder right now. And what we do is we ask the question about, so there are charges in motion over here. And let's say that this area is some delta A, and the length is some d. So let's ask the question that if I were to construct a surface over here, what is the flux out of this surface? So our assumption is that there is, or the information that we have is that there is a charge density rho that is moving with velocity v. And the question that we are posing is, what is the amount of charge or we can also call it to be flux, and flux is something that we know very well by now, that is passing through the area delta A in time delta t. So the amount of charge, and let's represent it as some delta q, that is passing through this area delta A that we have drawn over there, would be all that would be able to go through that in this limited time delta t. So this would be equal to the charge density times the volume which is covered in that duration. We know the speed, and we know what the time window is, so we know the length. We multiply it with the corresponding area, and that is our flux. And there's nothing great about taking this area that we are considering to be perpendicular to the direction in which the charges are moving. We could have very well, in fact, again, these are things that has appeared in one or the other context. So let's say the slice of the area is not really perpendicular, but rather it is at an angle, and the charges are still moving like this. So this is, for instance, the direction of the velocity, and this is our normal to the area element. Let's say that the problem was this and not the first problem that we have drawn, and we immediately realize that nothing really has changed. All that we are going to do is we are going to look at the projection along the area element, and we are essentially done. So even if the problem was not of the first type, but rather a slight variant of that, so this makes it completely general now. So we can still write this charge. So let's say if the slice is at an angle. So again, we do the same thing. We have our charge density, we multiply it by the length, and then the only thing that we are doing is we are looking at the component in a certain direction. And if this angle over here is theta, so this will be equal. For that, we are going to write this delta A cosine of theta. Okay. I'm not spending too much time on this because these are things, calculations that we have done earlier also. So that's why I'm just moving a bit fast on this. I can rearrange this equation slightly. So I can write, I can take the delta t on the other side in the denominator. And since I have this cosine theta appearing, so I can write that part to be the dot product of the velocity with the normal to the area element. And of course, there is the area part over here. The left hand side, we just talked about it, what this quantity is. It is your current, right? It is charge per unit time. We can write this to be delta I right now, and we can integrate to get the entire contribution due to everything. That's the standard way of doing it. So by integrating out, I can write the current to be equal to, I have charge density times velocity. And just in the previous page, what we did was this quantity, the charge density times velocity, was the current density. So it is the current density. The symbol for that was J. And then, and we are integrating. So current is really the flux of the current density. And the source of the magnetic field that we have been talking about, in fact, we can, once we look at the forces and the way things are, we immediately realize that this quantity, the current density, it is the source of the magnetic field, just like as in the previous, in electrostatics, rho was the source of the electric field. Let us do a little bit more on this. So I hope that till here things are clear, and it's not terribly complicated. Okay. So what we have always, and one of the assumptions in all that we have been doing is that this velocity, it has been assumed to be a constant. If it was not assumed to be a constant, what would have happened was that there would be a variable current. Okay. So now let me change the picture slightly, even though this will work, but just to highlight a few things. So let's say you have some volume, and there is a surface that encloses the volume. And there are charges that are there inside the volume. So that I represent by a volume charge density. And for some reason, we are not going to worry about that reason right now, whatever that may be. For some reason, these charges are going to flow out of the volume. And I would like to calculate the total charge per unit volume, per unit time leaving the volume. I know that this is related to the quantity that we just calculated. So if the question is really, and again, let me write it for completeness, the total charge per unit time, which is really the current, leaving the volume. Let's say this volume is V. This is equal to, so we'll not put an equal to sign here, but just let me put a colon over here. This would be equal to the flux that we have just calculated, but now we are talking about a closed or a volume, a surface which encloses this volume. So it's a closed thing in itself. So to capture that part, I'm just going to, for this surface, I'm going to put a closed surface integral. So this is surface integral. And then my flux. Okay. So I hope this is clear, that the picture that we have in our mind, it is really the flux. For some reason, the charges are moving out of a volume. Since the charges are moving out of a volume, this leads to current. We want to know what is the total charge per unit time that is leaving the volume, and this has to be related to the flux. Right? There is no other way in which the charges could have gone out of the volume. And this is a quantity that we just calculated in the previous page, what that flux was going to be. And that is related to the current density. Since this is a closed surface integral, again, I can take advantage of the divergence theorem and write to V equal to divergence of J. So great, I know what this flux is going to be. But also realize that this being a closed system in itself, and the meaning of closed system here is that I'm not really putting in additional charges, trying to build up new charges, nothing like that sort is happening. There was, so you can think of it as a fluid picture also, that there is water that is contained in a closed container, and then there are these pores, there's a certain pressure, and because of that, things are moving out. So because it is moving out, the water that is inside the container, it is going to go down, the amount of water that was there. The same thing will apply to these charges also. Because there is this outward motion, the charge density within the container or this closed or this volume is going to go down. So now, whatever we have calculated, because that is the outward motion, that is also related to the reduction that is happening or the change that is happening in the charge density or the charges per unit time. So the rate at which the charges are changing inside the container, since I have information about the volume charge density, I am going to write it as rho d tau. This change per unit time, how much that changes, that is the negative of what has already flown out. So from these two, I can write d rho d tau. Okay. I can take the derivative inside the integration. That would be negative of this divergence. And just by, again, comparing, I can write both of these are left-hand side and right-hand side are volume integral. So the rate of change of the charge density, that is equal to negative the divergence of the current density. You can take it on the other side. And set the right hand side to be equal to 0. What this expression tells you, and it is not hard to imagine what it is trying to say, it is trying to essentially say that the total number of charges in the system, this being a closed system, it is always going to be conserved. So the amount that changes within is the same as the amount that has flown out. So there are no charges that have disappeared suddenly within the volume. And it does have a name. This is what you call the continuity equation. Okay, and this is about conservation. So this is a conservation equation also. Conservation of charge. But go back to the problem that we have started with. We talked about these infinite current carrying wires. Was there any reason for us to even start there? And all our experiments or the experimental observations were based on this infinite current carrying wire. When I say that it is an infinite current carrying wire, there are really no sources or sinks that are present over there. So it's not that there would be a current drop suddenly and the current would stop flowing. So there is this continuous current, or steady current, which is always going to be there. So all our experiments, in fact, had to do with steady currents. And in this expression that we have just obtained, if the current were to be steady, what it implies is that the charge density remains the same at all times or constant. If the charge density remains the same at all times, then its time derivative is going to be equal to 0. So for steady currents, I can immediately argue that this quantity is going to be 0, which also implies that the divergence of the current density, that is equal to 0. When one thinks about this, what you call magnetostatics. So the previous problem was electrostatics, where what remained static was the charge itself. For magnetostatics, in fact, now I am using the title of the topic that we are getting into. The realm in which it is valid has to do with steady currents. Mathematically, what it implies is that the divergence of the current density, that is going to be equal to 0. Hope that it is clear till over here. So this has to do with steady currents. If the currents were not steady, that would be the next topic once we are done with this. So the word static in magnetostatics, what remains static over there, or rather steady over there, is the current itself. Okay. Hope that this point is clear, and this is the key at this point of time. So even though we took a different route and we talked about equation of continuity is a very powerful equation again in itself. It doesn't only come, because you can think about it from the discussion itself, that even if you are trying to construct mathematical expressions for fluids in motion, and if it is a system which is closed in itself, then a similar kind of equation which gives you a conserved quantity would appear there also. So it appears in a variety of places, And just like we have conservation equations when we thought about these conserved systems in mechanics, these would be the counterpart in systems where there is a steady flow. Okay, so now everything is fine, everything is in place. We know how to calculate the force, we know how to calculate the, or we know what is the assumption under which everything works fine. So now let's get back to the earlier question, which was, or rather the earlier thought that we have, not really a question at that point of time. And let me go a few pages back. So we said that the object is to calculate force. There are two parts when we are thinking about force. You can think of them as the cause and effect problem. The cause is the one which in fact leads to the effect. So these are two different objects in the manner that we are trying to think about. So we can make the problem disjoint over here. And we only worry about the first part. Because if we have information about the first part, which is the one that is creating something, which leads to a force on the other object, we are essentially done with the problem. So now with having done all these things and having talked about all these things, it again boils down to the same problem that we had earlier, and which has to do with how to calculate the magnetic field. And like we did in the case of electric fields, we don't have much intuitive theoretical basis to start with. We can talk about how this is, what is the effect at different points in space given different kinds of objects, but really we don't have much beyond that. We cannot come up with a really rigorous proof starting from first principles at this point of time. So what we'll do is we'll go to directly to something that we know, and this is a law in itself, which goes with the name of Biot and Savart. Okay. Often we call it as Biot-Savart law, but that's not the correct pronunciation. It's Biot and Savart. And let's say that you have some current carrying wire. This is again our coordinate system, the Cartesian, Z, Y, and X. It's this current carrying wire that is trying to produce this field, or that produces this field. Okay, and something that I didn't stress too much, maybe I should have, in the first set of experimental observations that we talked about, since the effects are really the same, whether you bring a magnet close to a current carrying wire or if you have two parallel current carrying wires, the effect on the magnet due to the current carrying wire is the same as the current carrying wire produces on another current carrying wire. And since these are two are the same, we say that these charges in motion, which should be now clear from the equation of continuity and the other discussion, that also creates a magnetic field. So we look at a very simple object, that is a current carrying wire, and calculate the magnetic field at some point in space. We do the usual thing, the location. So we start with a small element, let's call it some dl prime. The primed part is always to look for the location of the source, the point of observation from the origin of the coordinate system, that is the other r without the prime, and then this is the script r. So this is the standard way in which we represent these different things. And let's also not just think about a wire. Maybe I'm going to just finish the loop because we are thinking about steady currents. If you just have a simple finite wire, it won't make sense. So what the law essentially gives to you is we can write it as B equals mu naught over 4 pi. The current is I. So the current that is flowing is I. Its cross product with a unit vector that points from the element to the point of observation. It is still an inverse square, distance squared law. And then we are integrating over the entire wire, and so we integrate out over dl prime. Or what you can write it to be just by, again, the same argument that the current and the line element are in the same direction. So you can write it to be equal to mu naught I by 4 pi dl prime crossed into r by r square. This mu naught that you see over here, that is the permeability. And its value is 4 pi times 10 to the negative 7 Newton per ampere square. The units of the magnetic field is Tesla. But typically what we see is that the units in usage is the Gauss, where 1 Gauss is equal to 10 to the negative 4 Tesla. Tesla represented as T. 1 Tesla is a really large number. You may want to think about that. For example, the Earth's magnetic field is only half of a Gauss. Okay, so it's 5 times 10 to the negative 5 Tesla, for instance. So one Tesla is really extremely strong now. And this then becomes the starting point. Okay. The other units, before I get into that, the other units, just by looking at the way these are, you can in fact write other units as Newton, since you have current, so Coulomb per second, and then meter, which sometimes you also write as Newton per ampere meter. All these are valid units, okay? Because by now you know in the exam we do look for all these things. So make sure that you know all the units quite well. So now this becomes a starting point, just as well it was the case in the case of when we talked about electrostatics. And there are a few problems of interest over here. Maybe I'll take one or two of them, but there are two, in fact, that you should certainly know of. So the first example is the infinite current carrying wire. When you do these examples, also always compare with what is happening if you had only an electrostatic situation. For instance, if you had a simple line charge density, what would have happened? So let's say that I have, and this was my starting point. So this is basically the building block, just like a single charge was over there. Infinite current carrying wire is the building block for our purposes. So let's say that I have an infinite current carrying wire, which is along the Z direction. I'll keep the problem to be very simple. No point in getting lost in too many symbols and calculational details. Let's say that this is the y-axis. Let's say that I want to calculate the field at a point P1, which lies on the y-axis. So its coordinates were, for instance, are 0, y0. So as we just had, we take a small line element. So this dl prime, this is some small, I call it element, which I call dz in the z direction. Let's say this location of this element is 0, 0, z. So it's along the z axis. And then what we are trying to do is we are trying to, or the other input that we need is essentially this vector r. So this vector r would be equal to y hat minus z hat. The unit vector, these are straightforward things. We have done it enough number of times now. Divided by square root of y square plus z square. So if you recall in fact, let's write it one more time over here. The formula that we are trying to work with, this is mu naught I over 4 pi prime over r square. So now what I need to know is what is this quantity. And that is quite straightforward because these are simple cross products that I know quite well how to calculate. This is dz cross into the unit vector, which is y hat minus z hat divided by y square plus z square and the square root of that. So this would be equal to, I'm not going to again spend too much time. This is equal to dz y, that is the first term. You have a z hat cross y hat, which is the negative x hat direction. And then whatever we had in the denominator. So everything is now very well set for us, and we are in a position to calculate the magnetic field. So the magnetic field is going to be equal to mu naught I over 4 pi. We input all the other things. So I think I'll have to, I don't remember the result offhand, but the direction will come minus x hat. The other term doesn't come. I hope that you realize immediately because it's a cross product of the same unit vector or the same direction. So it would be y dz divided by, now you have a y square plus z square. 3 by 2. It runs from minus infinity to infinity. And then you do the standard trick. You do we write maybe z is equal to y tan theta, do this normal substitution and move on from there. So eventually, ultimately, when everything is done, so let me not write all those steps and bore you with these details, but remember how to solve these integrals. These are some things that you have learned early on. So finally, and I think this would be the correct answer, by 2 pi, I know that there will be a y in the denominator, and then it's in the negative x direction. So essentially what I'm saying is that it is going to point downward, and if I had another point which was symmetrically located on the other side, it would have come out. We know all this to be true also because the direction in fact is the right hand thumb rule. So that is something that we know of quite well. In fact, without proving anything, just by looking at the way the final result is, I can say that most generally what is going to happen is that, so we can think in terms of cylindrical coordinates because that's how this direction of the magnetic field is going to be. So most generally what I can write, if you want, you can in your own free time you can try to in fact get the most general expression, but I don't expect the form to differ in any way because it's just going to be symmetrical like this, right? It's just the magnetic field is going to be like this. So this would be equal to mu naught I 2 pi s, and the direction is really the phi hat direction, where this phi hat, if you recall, this is the cylindrical coordinate system that we are talking about. This was minus sine phi in the x plus cos phi in the y. Okay, and s square, this was x square plus y square. The thing that you should make a note of, something that I said, that if we were going to calculate the electric field, if the line charge density was lambda, so I think the result was lambda was equal to 2 pi. I might have missed factor. No, everything is fine. S in the s direction. So dependence on the distance wise, nothing has changed, and that should have been given the way the law itself is said. That should not come as a surprise. It's the direction which is different, and this also brings out the different nature of the two fields in themselves. Okay. So although that there is a marked similarity between these two different expressions, in the sense that they both depend inversely on the distance, still the way in which these fields are, they are going to be quite different. Having done this calculation, the experimental observation that we started with that becomes just natural. So explaining that by going through all these different methods, and this is how everything gets tied up, is our starting point was in fact two current carrying wires. Let's say one carries a current I1 and the other carries a current I2. So if I were to calculate the magnetic field for this, let me write here F magnetic. This would be equal to, so let's say I want to calculate it over here or on the other side, whichever way. So let's calculate it over here. So it would be I1 dl cross B. We just calculated what this B is going to be. In fact, the magnetic field is going to come out, and let's say this direction is our X direction. So it would be equal to I1 dl cross mu naught I divided by, let's say that this separation is some distance d, so 2 pi d, and the direction is simply going to be the X direction in the way that it has been set up. So I know everything. It should not be a very hard thing to do. DL is in fact dz in the z direction. So having done all those things, putting in all these inputs, I2 over here, so it would be equal to mu naught I1 I2 divided by 2 pi d, and you have a, so you have to worry about your two directions. I hope that I have taken the directions properly. So one is z and the other is x. So I have a z cross x, which is the negative y direction. And then there is this integral over dz. I cannot really do this integral in the limits minus infinity to infinity, but just to get a basic idea, I'm going to, instead of calculating the force, I'm going to calculate the force per unit length. And in fact, this would be equal to force per unit length. This would be equal to mu naught I1 I2 divided by 2 pi d in the negative y direction. So now everything falls in place, because we know that if it was, the current was along the same direction, the force has to be attractive. And whether it is an empirical way of looking at it, whether we have tried to argue about how to come up with such kind of equations, it ties up nicely with our experimental observations, and that is the most important part. The second problem, I'm not going to solve it. I do realize that me standing and solving doesn't help in any way, but and also it may turn out to be not very interesting, but you should in principle know. So let me call it example 2. This is the current carrying loop. In fact, if you think about it, this is one of the most natural geometries to think of, because this is something which is infinite current, always steady currents will be there. And also later you will realize that this becomes just like we had the dipole moments or the dipoles in the case of materials. In the same way, when we talk about magnetic materials, the simplest building block will be the current carrying loops. And there are objects like magnetic moments, which we'll talk about. But what I want you to, and this you should try on your own, let me not do it. Think of a current carrying loop and calculate the magnetic field at a point situated above its center. What you should, once you have done the entire calculation, what you should get is the magnitude of the magnetic field for points which are the observation points which are very, very far away from the center of this current carrying loop, that should go as 1 over z cubed. There will be some term in the numerator. This is something that I want you to look at. Or maybe at a later point of time, I might just pick up these things. And what the term will have in the numerator, so the numerator, apart from other things, that's not the only thing, that will have a area. Let's say the radius is some a, so pi a square times I. And the direction you may want to think about. But what you should notice is that this dependence that you observe, there is a quantity in the numerator which has to do with the area of this loop times the component that is responsible for the magnetic field itself. This later, we'll give it a name right now, but we'll use it later. This is what you call the magnetic moment. It will also have a direction. So those things in detail later. And this dependence on inverse dependence on z cube, that is very, very similar to what you had in the case of electric dipoles. If you go back and look at the expression over there, I'm not going to write it, but the electric field, let's say along some point, I call it some z, just to make sure that it has the same thing as in the previous in the loop example. That would go as, there would be this quantity p, which is the dipole moment. There will be an inverse dependence. On purpose, I'm not writing the complete expression, and it will point along the direction. So just like this basic element of two charges separated by a distance is what we call the electric dipole, the current loop is what we call the magnetic dipole. We'll take it forward from here, but I would say that at least these two examples you should know how to solve. Go through the entire thing, see how those unit vectors and other things play out. Try to solve it in Cartesian as well as in the cylindrical coordinate system, and see if there is something hidden over there. Okay, so these are just pointers we want to think about. Let me stop with my presentation. I am out of time now. If you have any question, feel free to ask. This is a natural stopping point also.